Okay, we're going to start with the chapter 5. And the chapter 5 is an application of the chapter 4, which is about how the force can create a motion and can stop a motion. So we're going to focus on two things. The first part of the chapter 5 talking about the friction force. The second part of the chapter 5 talking about a special kind of a motion, which is the circular motion. So in this part, we're going to look at the friction force. The friction force has a very interesting phenomena, and we're going to discuss that in this chapter here. Before we get into this, I wanted to quickly review what we did in the chapter 4. It's a very important concept that we introduced in the chapter 4, which is the free body diagram. In order to analyze any kind of motion, the free body diagram helps us to identify all the forces acting on the object. And you will see the friction force is a little bit tricky as opposed to the rest of the force, because most of the force has a very special direction. Well, friction also have a very special direction, but the friction force direction can change, depends on how things is moved. So the free body diagram can resolve of the two different kinds of motion. One kind of motion is at the rest or moving at a constant velocity. When you have that situation, is the first law. So the Newton's first law to simplify that is just simply the net force equal to 0. That is the case that you have the Newton's first law. When you have the net force equal to 0, that means you are at the rest or a constant velocity. Don't forget about the constant velocity. This is also valid in the first law. If the net force is not equal to 0, that is what our second law is going to be applied. Then your net force is equal to the mass times acceleration. Most of the time, if you have the second case, then we can start from the acceleration. We can analyze the motion in different way, such that we can say, you know, how much distance will the object move in a certain period of time, and what is the speed after like 10 seconds if you have an acceleration be pushing by a force. Or we can also ask you, you know, how much time does it needed that we are going to push this object to, say, 1 meter. So you're going to incorporate with the kinematics equations to find out those information. Newton's third law is also important in the free body diagram, because when we look at the free body diagram, we try to isolate an object. Whenever you isolate an object, it's like you are taking the object out of the interaction. When you take things out of an interaction, you have to remember that you put that interaction force, which is the force coming from the other object, applied to the object that you are interested. So the Newton's third law is about the action and reaction. They have the same amount, but with the opposite direction. All right, so understand that, then let's look at the friction case. And you're going to see me drawing some of the free body diagram as well, and we will talk about the free body diagram over there too. Now, where is the friction coming from? When you look at the picture that we have over here, the first picture that we show, just a simple like a card on top of maybe like a plank. Now, if you give a force, let's say the force going to the right, and you try to make it move to the right. And if you magnify the interface between the box and also the ground plank, you will find out if they're not very like ideally smooth, they're always going to have some like a roughness, and this roughness going to create certain like spikes in certain place is going to go down with like a small hole, and they are like a rub against each other when you pull it to the one direction. If the object moving to the right direction, what happened is in the, let's say, particularly for this part, when you move to the right, it eventually going to hit on this peak on the ground. When they hit with each other, you're going to create a direct contact. This direct contact is going to create an action and reaction. So you try to push to the right, but however, the ground is going to push it back. And you have hundreds and thousands of these things happening, and the magnitude of that is all different. So microscopically, the roughness of the surface is going to give you a very hundred and millions of very small normal force try to stop this object from moving. That force is our friction force. And that force, because it's against how things is moving, so the friction force is always going to be the opposite direction of the motion. So this is important how we actually identify the direction of the friction force is that friction force is always opposite to the direction of the motion. If the object moves to the right, friction go to the left. If object going upwards, friction going downwards. If the object going downwards, then friction going upwards. So this is always the case that your friction is going to be. Now, interesting things about this is that we have different kind of a friction force. And particularly for the solid, if you have two solids and they are in contact with each other, then we might have a case called static friction. We also have a possibility is going to have a dynamic friction. The static friction probably is easy to understand. If you have an object on the ground, you just lightly touch it, it's not going to move. You keep on increasing your force, it's not moving at all. That is what we call the static friction. Static friction meaning the object is not moving, but you still have the friction force. That is the static friction. So no motion, when you have no motion, that is your friction force. But if things start to move, if let's say, for example, this box that you see in this picture, if the box moves to the right, and even though it's moving, it doesn't mean there's no friction. The friction is always there, right? So when things start to move, then you are going to have the friction force as well. And that friction force is what we call the dynamic friction, or sometimes we call kinetic friction. So you have a motion, and that force is opposite to where it moves. If you're looking at a case where the object is not like solid, they are like a fluid, such as the air, or even in the water, you're going to have a resistance. That resistant force is another kind of a friction, but the friction is due to the air particle or the fluid particle, And that kind of force is what we call the drag force. We're not going to emphasize on the drag force a lot. And there's like an equation in the chapter 5.5. We will briefly talk about that next time. But remember, drag force is another kind of a friction force. How do we measure the friction force? Well, let me just show you these two pictures over here. On the left-hand side, this one is a force gauge. And it would be very similar to the weight scale that you see in the grocery store. If you use that gauge hand with another block on another like a surface, where the surface is rough, then you slightly pull the force gauge to the right, then what happened? Well, if you put it with a small force, this block probably will not move. Not until you pour it with a larger amount, otherwise it's not going to move at all, right? So you can measure the friction force by this way. Another way you can measure the friction force is on the right-hand side. You can put a block on top of another, like a surface, a rough surface, then you like slowly increase the incline angle. If the angle is small, it's almost like a flat, it's not going to move, but when you increase the angle, and you can do it by yourself, at a certain point, it's going to slide down. And why is that? And how do we analyze that? Is probably the most important topics for this chapter. So make sure that you understand how we analyze these two situations, and we're going to show you the example as well. Okay, now the next one that I was showing you is an important concept about the static friction and the kinetic friction, or the dynamic friction. In this picture over here, we have two objects. On the left-hand side is called impending motion. Impending motion simply said this object is not moving at all, but it has a tendency to try to move. So it's impending right now. On the right-hand side is that things start to move. So you can see the motion is over here, tell you the direction of the motion is going to the right. The picture shows you the free body diagram for both cases. And if you look at that, we're looking at a block. So when you do a free body diagram, we isolate an object. In this case, the object that we are isolating is this one, is this block over here. We are interested about what are the forces acting on this block and how would this block move. This one is the first law. So static meaning the first law, where the first law in this case is at the rest. If this is at the rest, then that means all the net force has to be equal to 0. So think about how we measure the friction force using the force gauge. If I start to pull the force gauge, let's say I start with 1 Newton, the object doesn't move. I increase my force to 2 Newton. Well, it's still very small. The object still not moving. Then until I pull it to like 10 Newton, it starts to try to move. And then you think back, if I start with 1 Newton, what is the friction force in that case? If object doesn't move, that means the force has to be balanced. And you look at the free body diagram, horizontally they are only, this is a pulling force, and this is your friction force. If things doesn't move, that means these two forces has to be equal. If you give 1 Newton, the friction force will be 1. If you give 3 Newton and things doesn't move, that should be friction force equal to 3, etc., right? So the friction force, the static friction force is not a constant value. It depends on how much force that you apply to the object. And it's going to be proportional to how much force that you apply to it, right? So the amount of the friction force is actually equal to the net force along that same direction. In this case, is the pulling force itself. The graphically, you can see that we make a graph like this. And we just write this equation here. It tells you if you are in a static region which things doesn't move, and well, it's also possible to move, but it's going to move at a constant velocity. But just think about at the rest, it will be easier to image. And then the friction force is proportional to the applied force. There is a maximum point, which this maximum point is the point that we are more interested. If you start to pull this object with the force gauge until a certain amount, the object start to move, and we will call this force to be the maximum static friction force, which is this one here. And we can quantify this by this equation over here. This equation gives us the force is equal to the mu. This one is the Greek, the mu. Mu s times the n. So what does the mu s represent? What does the n represent? The mu s is this coefficient. It's a number. It doesn't have a unit. It's called the static friction coefficient. This number depends on how rough the surface between the object and the other object. So it represents how harder to make it move. The roughness of the surface is going to change how easy or how hard it will move. So no unit, and it's just a constant. This constant is going to be less than 1. It's going to be like a 0 point something or 0.0 something, depends on how smooth or how rough that is. What about n? Well, n is our normal force, is this n over here. And this normal force is the normal force between these two objects, okay? So you can find this if you are given with the static friction coefficient, then you find out the normal force, then you can find out what is the maximum static friction force is. And another interesting thing about this is once this thing starts to move, then we find out it will goes to a very, like a number, which is very like a constant. So this Fk over here represents the kinetic friction force. This force also similar to the static friction force depends on a constant, which is a mu sub k, and that is the kinetic friction coefficient. It also depends on the normal force between the two objects as well. Okay, so on this right-hand region, it's going to be a constant. This one is a constant. The static friction coefficient is not a constant. It depends on how much force that you actually apply to it. And there's a maximum value for that. So that's the most important part about the friction force. Let me show you some of the example to tell you how we can calculate these things And let me write down the two equations that you saw before. Static friction force has a maximum. This maximum is equal to mu sub s times the n. The kinetic friction force is not, there's no like maximum, but this is a mu sub k times the n. They all depends on the normal force. And the mu and mu s are all less than 1. And also the mu s is going to be greater than mu sub k by looking at the graph that you will see, right? So these are the difference between these two. Okay, look at the first example. I have a block and it's on the flat ground with a friction, and it give you the mu s, mu k, which are the coefficient of the friction. And we wanted to see what happened to the friction between these two objects. The first question we wanted to know is how much force needed to make it move. So let me make a drawing here. The flat ground, and it's rough, so it has a friction. I have a block here. This block is 10 kilograms. And if we want to make it move, let's say I have a pulling force. This is a pulling force. I need to know how much this one will make it move. Okay, so what is the thing we try to ask in this case? Are we looking at the static friction force? Or are we looking at the kinetic friction force? Well, think about that you're pulling an object slowly, and as we said, when you pull with a small force, it's not going to move, and that force is what we call static friction force. So until you pull it with a larger enough and larger to, the force is going to be greater than the F of S of the maximum, then you will start to move. So what the problem one is trying to ask is, what is the F of S a maximum such that it will start to move? Because this Fs maximum is this friction force, where the Fs represent the friction force, and when you have the pulling force which is greater or equal, it will start to move. Okay, so when you have that one is greater or equal to that maximum friction force, it will start to move. So we try to find what is the P, and simply just try to find what is the Fs of maximum. And then you look at the equation is equal to mu sub s times n. And you're given with the mu sub s, this one is equal to 0.3. But then the next question is, what is the n? How do we find the n? Then you have to look at the free body diagram. So again, this one that you just saw it from the previous page, you are going to have a normal force here, perpendicular to the contact surface. This one has a mass, so it also have a weight. So this is the weight of the object. And if we look at the y direction, I can write at the y direction, there's no motion, so you have to have the balance of the force. The W, the M minus W is the net force has to be equal to 0, which is the first law. And what I tell you is your normal force is simply equal to the weight. And please don't write the weight is equal to 10. 10 is the mass. A lot of people make mistake in this point. This weight is the mass times the G that is your weight. So this is a 98.1 Newton. Okay, and then you can find out your F as a maximum that is equal to 0.3 times 98.1 Newton, and that is your pulling force needed to make a move. Okay, so that's your question 1. So let's look at the question 2. Will this object move if we push it with 10 Newton? Well, I guess we have to calculate this. Let me calculate this one. This will be equal to 29.4 Newton. Let me make this one with the 3 sig fix. So I use the 3 sig for this one here. So the maximum is 29.4. Then if you push it with 10 Newton, would it move? No, because your force is less than the maximum. So it's like you are pulling it slowly and it's not larger enough, it's not going to move. If it's not moving, then what is the friction force? Is the friction force equal to 29.4? No, if the friction force is 29.4, if this one is 29.4, your pulling force is 10 Newton, then the net force is not equal to 0, it will start to move. So if you are pulling with a 10 Newton, the friction force is also going to be 10 Newton because it doesn't move horizontally. You pull 10 force to the right, friction goes to the left with the same amount. That's why we say friction force, static friction force is not constant. So if we increase this force to 50 Newton, then what happened? Well, the 50 Newton is greater than 29.4 Newton, so it will start to move. And what is the direction of the motion? It will go to the net force direction. So the net force, if the pulling force is larger, so it's going to the right. Right? It will move to the right. Then in that case, because it's moving, then what is the friction force? You have to use kinetic friction force. That is your friction force. And how do we calculate this friction force? Again, it depends on the normal force. So, but the constant is going to be 0.200 and multiply with the normal force, where the normal force is going to be the same as well, then that's 98.1 Newton. And then you calculate this one. There will be 19.6 Newton. So that will be your friction force. This is going to be a constant. If you apply a certain amount of force, then this will be always going to be the same. The last thing over here we're looking at is, what about if we push it with 100 Newton and I say it will move? Certainly it will move because it's greater than 29.4. We want to find out what is the acceleration of the block. And how do we find out that? Then you look at the block again. The block is going to, in this case, is going to have a motion, and we just isolate the block. This is the block itself. We have a normal force. This normal force is equal to the W that we just found out previously. This is a W. And we have a friction force. This is the friction force go to the left. This friction force is going to be kinetic friction force. We also have a pulling force. This pulling force is 100 Newton, and that is given from the problem. Okay, so how much is the kinetic friction force? Well, we just did it. This is your kinetic friction force because we said this is going to be a constant. As long as the force is greater than the Fs maximum, this force is always going to be the same. This is 19.6 Newton. Now the things will move is only move to the right, so I can use the second law. The second law tells me the net force equal to the mass times the acceleration. And what is my net force? If I make going to the right to be positive, then I have 100 Newton minus the friction force 19.6 Newton. And as the only two forces has to be equal to the mass times acceleration. And what is the mass? The mass is 10 kilogram. And you multiply with the acceleration, then you can find out the acceleration. So the acceleration will be equal to the 100 minus 19.6, that will be about 80.4 Newton divided by 10 kilogram. That will give you like 8.04 meter per second square. So that's your acceleration to the right. Now, if you know the acceleration, can you find out what the distance would move after 1 second? Then you have to use the kinematic equation. Kinematic equation, if you have acceleration, a constant acceleration motion, the change of the distance, the x final equal to x0 plus the v0 times t plus 1/2 the acceleration and t squared. Now, initially, the velocity is equal to 0, so you don't need to worry about this. Initially, let's say initially is at the position of 0, then I don't really need to care about this as well. Then the distance is simply equal to 1/2 at squared, which will be 1/2 8.04, and t is 1 second, and that will be 4.02 meter. And that is how you apply this to do the calculation of the friction. I'm going to put some more example in another video, but this is going to be the lecture for the friction. Now, we didn't talk about the drag. We will briefly talk about that in the next lecture.